Today I'm going to talk about electromagnetic waves. The reason I'm making this video is because if you study electromagnetic waves, you are likely to come across a diagram that looks something like this. And this shows an electric field going up and down and a magnetic field going back and forth and the wave traveling in some direction. And I found that people are actually confused by this because they think this is a three-dimensional diagram of what electromagnetic waves would look like if we could see them. And so they think that an electromagnetic wave is confined to some space and there's something going up and down and something going back and forth. And then when we try to explain how antennas work and how waves propagate, they don't quite understand, well, how does this wave, know how to get from this antenna to that antenna? Well, how does it know which direction to go? Because it appears to be something confined to a finite space. And although this is a useful diagram for some purposes, it is not a 3D visualization of what an electromagnetic wave would look like if we could see them. So let's talk about what waves are, what this diagram represents, and then what electromagnetic waves would look like if we could see them. So first of all, when we talk about waves, we might be talking about one of two related but different things. One type of wave is what we get when we have an oscillator or some other piece of electric equipment that produces what we call waves. So what happens is we have a voltage that is going up and down and up and down. So we have it going up to some voltage, let's say like what comes out of the wall in America. I know the numbers. That's going to go up to about positive 165 volts down to negative 165 volts. And the RMS voltage is going to be around 117 or so. So there's a voltage going up and down over time. This cycles 60 times every second. In most of the world, it's going to be a higher voltage, more like 220, 240, and the frequency will be 50 times a second, but still it would look pretty much the same if we looked at this on an oscilloscope. So an oscilloscope shows us how voltage changes over time. So as time goes by, we see that voltage go up and down and up and down, and does that up and down cycle 60 times every second in North America and a few other places. But in most of the world that would be 50 times every second. So a wave is simply a changing voltage, maybe a changing current or something like that, but usually we're just talking about a changing voltage over time. And how do you visualize that? Well, there's nothing to really visualize other than we can put that on an oscilloscope, which will trace that out over time. So we call this a wave because it looks like a wave in the ocean or a wave on a pond. So we call them waves, and there is a relationship because there's a frequency. Waves would have frequencies as they pass by. It has an amplitude, how big is it, and other aspects that are the same. So they are related, but the other kind of wave is a physical entity that trades kinetic energy for potential energy and radiates away from some source that causes this wave. So let's take a look at a typical kind of wave. So let's say we have a pond. Here's the surface of the pond. There's no wind, there's no seismic activity nearby, and so the surface of that pond, pretend that this is flat, is perfectly smooth, and there's no energy imbalance. But what we do have is gravity pulling the water down towards the earth, but we also have hydraulic pressure that's pushing the water upwards, and they are in equilibrium all across this pond. And so the surface of the pond is flat. But let's say we now drop a rock into this pond. So that rock is going to come down. It's going to drag some water down with it. And that's going to cause an imbalance. And as this water is dragged down and it pushes water away, well, water is virtually incompressible. So the water can't become more dense. So it is actually pushed up along the edges. It's a crude drawing, but you get the idea. So we get the water pushed away, and the pressure causes it to push up away from gravity, and gravity wants to pull it back down. And so gravity does pull that back down, but as it does, it pushes on the water, which causes the wave to propagate outwards. I don't want to get into too much detail analyzing exactly what goes on, but we end up with a wave that looks sort of like that. So we have troughs and peaks, and that travels away from the initial source. So we get what you expect: drop a rock into a pond, you get waves that travel in circles away from that. And a cross section would look something like this. And as we get further away, that wave diminishes as the energy is spread out over more and more area, and eventually it's not detectable. And eventually this would dissipate to the point where we're back to our smooth surface again. So what we have is a trade between potential energy, where this is pushed up. Gravity wants to pull it back down, and so it's going to pull it back down. And as it's pulling down, it's going to move, and we get kinetic energy. So the wave goes up to a potential energy point. Then as the water moves back down, we end up with kinetic energy. And of course, it's going to eventually overshoot and go down. And now we have hydraulic pressure pushing it back up. And now we have potential energy wanting to push it back up again. It's going to overshoot. And we get what we call waves. Sometimes they're called gravity waves, although that could be confused with gravity waves like we have recently discovered coming from astronomical events, which are waves in gravity itself. So it's a slightly different thing, but these are typically caused by gravity. But there's other similar types of waves, like sound waves or pressure waves, and they, instead of having something visual we can look at like this, a sound wave would be, let's say we have a source of a sound wave, I'll call it a little circle of source, and it expands, so it compresses the air around it, gets it more dense, then it contracts, then it makes it less dense, and that dense air is going to expand around. It's going to push into the air around it, and that's going to push into the air around it, and that's going to have rings of denser and less dense air expanding from there. And that's an important thing to look at right now, because here we have a surface wave that only works on a two-dimensional surface. Of course, it's 3 dimensions, but it travels only in 2 dimensions. This sound wave, the compression wave, would travel in 3 dimensions. Okay, so that's a different kind of wave. So one type of wave is what you can see on an oscilloscope as a voltage goes up and down, and another type of wave would be something physical, such as the surface wave on a pond or a sound wave. So an electromagnetic wave is related to the second type, and if we have a source of electromagnetic waves, like the sound wave, instead of traveling like on the surface of a pond, an electromagnetic wave is going to travel away in a sphere. So if I have some source of electromagnetic waves, that could be an electron that drops from one energy state to another and produces a light wave, and that would travel away as a sphere from that electron. And I thought light was particles. If we get down into it, it's a little more complicated than that. But when we get down to the quantum level, light is not really a particle. It's a wave function that can act like a particle. So that wave would go out in all directions, and I have other videos talking about the wave-particle duality, which I don't want to get into now, but why it sometimes looks like a wave, sometimes looks like a particle, and it's really a wave that has characteristics that can look like a particle. So that's what we have there. So let's back up. We have something that creates these waves, and they go out in a sphere. And another thing that can create a wave is an antenna. So let's say we have a piece of wire and we energize it by putting some electricity into it. I don't want to go into details about that too much here. I have whole videos on how antennas work. But we put a little energy in there and we have a wave of electrical energy that travels along that wire, hits the end. It can't go anywhere else, so it bunches up and creates a voltage. And that voltage pushes the electrons back down the other way, and then they hit the other end and they bunch up again. And so we have voltage in the ends, but in the middle where the wave is going back and forth along this wire, a wave of electrons, we end up with current going back and forth. And that disturbs the electric equilibrium of, well, I've got to be careful how I say this because distortions in space-time are gravity, but we have distortions in quantum fields that we call an electric field. And those moving electrons cause disturbances in that. Does that sound familiar? We have quantum electric fields that barring some disturbance, are equal and evenly distributed and uniform, but we get an electric current going back and forth somewhere, that's going to disturb those quantum fields and cause a wave of energy to move through that quantum field. Now, a simple wire like this would not create a spherical wave because physics, I explained this in another video, the waves will tend to travel away from that antenna perpendicularly to the orientation. So we get waves that not quite like the pond because they're not going to travel only in those directions, but that'll travel a little less in that direction, a little less in that direction, a little less, and almost none perpendicular to it. So you can think of it like an expanding bubble, like we talked about the sound waves as like an expanding bubble. Same thing, but the bubble, I'll draw it over here, the bubble's more shaped like that, sort of like a toroid, a donut if you look down from the top. So it's expanding horizontally if the antenna is vertical, but if we look down at it, we're going to see it expanding in a ring. And so we get these two lobes of expanding electromagnetic energy. And so it's not quite spherical because most of the energy is concentrated in this direction and almost none in the vertical direction. But let's just, for simplicity, say we have a source that can create these radio waves that go out in a spherical way. So here's the source that creates them, and these radio waves will radiate out. And I'm just showing this in 2 dimensions, of course, because I have a whiteboard, but these are cross sections of bubbles of electromagnetic energy. So let's take a look at what those would look like if we could see them. So let's just take a look at one pulse of that. In other words, we have that current going up and down that's making disturbances in the electric quantum fields, and that's causing expanding bubbles of electromagnetic energy. Let's just look at one of those bubbles. Just look at the peak of the electrical energy at one point where it's at its greatest. And let's say that the orientation of the source, in other words, the direction the electric current is flowing, and the orientation of the antenna or whatever it is such that our voltage is highest that way and lowest that way. So if we could see this, and if we could see voltage, we would see that along the equator, it's basically 0 volts. Well, 0 volts compared to what? Well, 0 volts compared to itself, because as I mentioned in many other videos, voltage is meaningless unless you compare it to another voltage. And so we're going to say, well, our 0 is in the middle, so we get a higher voltage as we go up and a lower voltage as we go down. So we get this gradient of more and more positive voltage as we go up. And so the pole would be at the greatest positive voltage. At the equator would be 0 volts, because that's what we've designated 0 volts. If we had some instrument that could measure this, that's what we would do, is have our virtual voltmeter at the equator, and that's by definition 0 volts. But as we go further and further toward the south pole of this expanding bubble, we would find that at that pole we get the greatest negative voltage. And so let's say if we had some gradient, I'm going to just use some red ink here. In the middle is our 0 volts, but as we go more and more positive, it gets more and more concentrated positive, or should I say as we go upwards, we get more and more concentrated positive voltage. Very, very concentrated up here, but less and less toward that. And I'll just use the black because my green pen doesn't really show up on the camera very well. As we go down, we get more and more negative voltage, but as we get closer to the pole, it's more and more concentrated. So if you could see this as colors, we'd see the color get deeper in the positive color as we go toward the pole, and deeper in the negative color as we go to the opposite pole, and get a stronger and stronger field. But around the equator is where we would have our 0. So that's what that would look like. And of course, that's expanding outward. And right behind it is going to be another one. So this is a little difficult to draw because we're going to have bubbles inside bubbles, because we have one bubble expanding and then another one behind it and another one behind it. And each one will be opposite polarity. So the one behind that, if we could see it in there, it's going to get kind of cluttered in the drawing, but here's the next pulse coming out, and that's going to be negative at the top and positive at the bottom. And then behind that will be another one expanding inside that one, and that's going to be positive at the top and negative at the bottom. So if we could see these waves expanding, if we could see the polarity, that's what we would see, is this expanding bubble. Now, what do we have around the equator? Well, as this expands, we have an electric field expanding, and what do we get when we get a moving electric field? We get magnetism. I have a couple of videos, I'll have them linked in the description below, that explains the relationship between electricity and magnetism. It talks about moving electrons and positive charges that aren't moving, but they look like they're moving. And because of special relativity, we get an electric field that looks like a magnetic field. So electricity and magnetism are actually the same thing. A magnetic field is merely an electric field viewed from a different frame of reference. So from this frame of reference where I'm watching the spheres of electric energy expanding, I see electric fields. But if I surf on one of those expanding bubbles, I wouldn't see the electric field, I would see a magnetic field instead. So at the same time I have this electric field, I also have a magnetic field. Can you detect both at the same time? I don't know how I would test that. I don't know what instruments we could use, but I believe that we would only see an electric field. If we had something that could detect magnetic fields, well, guess what? We have a moving electric field. We're going to have a magnetic field associated with it, so naturally we would be able to detect that. But that, once again, that magnetic field is simply an electric field viewed from a different inertial frame of reference, a different relativistic frame of reference. So we have a magnetic field too. And that's going to go around the equator, and it's going to be sort of like a ring of magnets, where we're going to have north to one direction and south to the other direction. But if I can kind of draw this obliquely, I'm going to try to draw a bunch of little magnets here to represent that field. Let's see if I can kind of make this elliptical. Terrible drawing here, but I think you'll see the point. So these are a bunch of little magnets: north, south, north, south, north, south, north, south. I'm just going to make the north end black. So the north half is black, south half is white. And notice that as we go around the ring, the north is always the same direction and the south is up the opposite direction. And so that's sort of like a ring going around there. So it's not like the poles where we have positive at the pole and negative at the other pole. It's going to be like a whole bunch of little magnets, north, south, north, south, north, south, circling around that equator, where it's strongest around the equator, where this magnetic field goes around and round. And just remember that's nose to tail, north, south, north, south, north, south, north, south, north, south, as it goes around. So we have that north-south orientation this way, the positive negative orientation the other way. And as each of these rings expands, that magnetic field is also swapped, as well as the electric field. So that's what they would look like if you could see them. So that's what we see if we're looking at the source and we can see those spheres of electric fields expanding. We'd see the electric field and the magnetic field oriented like I have here. But what happens if you get further away? So as we get further and further away, let me do a quick drawing on the side of the board over here. Here's the source, and notice that as I get further and further away from that source, that this bubble is a bigger and bigger circle. And as we go further and further away, let's start further away and keep on going. And as we get further and further and further away, this is starting to look straighter and straighter. And eventually we get far enough away that the part of that sphere that we can see looks like a flat plane. So I'll draw some lines here. So here's our electric fields passing by in this direction. So if I'm standing here watching this, I'm going to see these electric fields coming at me and passing by me. And if I try to make these three-dimensional, if I can, let's give this a try. Just looking at part of them now. Don't get the idea that these are like flat pieces of something. They extend up and make a huge circle. We're just looking at part of it. So I'll just kind of dash these lines here to remind you. Actually, I have to dash them all because they're all part of the sphere. So I'll just leave them there. So we're just going to look at this one little part. I'm just trying to show you that we would see these coming as flat planes if we're far enough away. And what would we see? Well, we'd see, if this was, well, let's put this one right here, positive at the top, negative at the bottom. The next one coming at us would be negative at the top and positive at the bottom, positive to negative, negative to positive. And that's going to be assuming the orientation is such that we get our electric field in this vertical orientation. It could be rotated sideways. We have these vertical aligned electric fields coming one after the other. How far apart are they? Well, that depends on how often they're changing polarity. So if it's, let's say it's an AM radio antenna that's producing radiation at the middle of the AM radio band, which is exactly 1 megahertz, well, these would be a total between here and here would be 300 meters. So that would be the distance between each one of these if this is an AM radio wave. But if this is FM, which is 100 times as fast, 100 times the frequency, these would be only 3 meters apart. So same thing, but they're just closer together. I don't want to try to draw them closer together, but so if AM radio, they're 300 meters apart. FM radio, they would be 3 meters apart. So just closer together. But once again, top positive, bottom negative, top negative, bottom positive, as we see them rushing by us at the speed of light. And just don't forget that these are not just boards of energy, that they extend in a huge sphere. And how big is that sphere? It depends on how far away the source is. I mean, if these were coming from some star, then these spheres would be light years in diameter. So if this is a radio telescope looking at energy coming from a astronomical source, giant spheres of radiation, where we're just looking at one little part of it. So that's just what we're seeing as we see those fields come at us. We see a electric field oriented one way, and then we see another electric field oriented the other way, and then this way, and then this way. And of course, each one's associated with a magnetic field. So we have, let's say it's north and south. So north to the right, south to the left. The next one is going to be north to the left, south to the right. So if I could see this field coming at me, and it's just extending gazillions of miles in every direction, but what I see is I go higher, I get higher voltage or more positive voltage. I go lower, I get less positive or more negative voltage. To the right, I get north. To the left, I get south. And here comes the wave. It passes by. I'm slowing down time so I can see these coming, because of course they're coming at the speed of light. The next one comes. The polarity is reversed, so I have positive to the bottom, negative to the top, north to the left, south to the right, or vice versa, depending on how they started. Or if this is oriented the other way, I might have positive to the right, negative to the left, north to the top, and south to the bottom. So they can be oriented any direction. I'm just, for convenience, showing them vertically oriented with the electric field going up and down and the magnetic field going from side to side. So that's what the nature of an electromagnetic wave is these fields, and we would see them coming at us with an electric orientation one way and a magnetic orientation the other way, traveling toward us at the speed of light. How close together they are depends on the frequency, and I would just see these polarized electric fields just coming at me, coming at me, coming at me. So that's what an electromagnetic wave would look like if we could see them. Of course, I'm only looking at a bit of them. Just imagine that this just extends out gazillions of miles, or maybe a few miles, depending on if the radio transmitter's a few miles away or millions of miles away. Depends on how big these bubbles would be. But that's what they'd extend. They'd just extend to be big bubbles. So don't forget that this, if we zoom way, way out, we find that that's actually, see if I can make a drawing here. I'm actually looking at just part of a bubble that's radiating from a point, and there's one coming after the other. So how does this relate to this diagram? Well, let's figure that out. If we go back to our original type of wave, which is just a voltage going up and down over time, let's look at that on an oscilloscope. There's an oscilloscope screen, and I have a voltage that's going up and down and up and down and up and down, and as time goes by, we have our voltage going up and down and up and down. And whatever the settings of the oscilloscope are show us that this peak is maybe, it's like plus 12 volts, minus 12 volts. And it could be plus 12 and plus 3, whatever. But we have a voltage going up and down and up and down. And that's exactly what we have with the electromagnetic wave. Remember, if we look at that wave, as time goes by, that voltage is going to increase and then decrease. Then it's going to flip polarity and it's going to increase and decrease. So over time, we're going to see that electromagnetic wave go higher voltage, lower voltage. So if we plot that on an oscilloscope, we get this. So we have this voltage wave that is vertically oriented. So I'm just showing this, okay, this is vertical. I'm just drawing a vertical wave. But associated with that is going to be a magnetic wave. And how do I draw this? Well, I've got a flat thing. I'm going to have to do a three-dimensional drawing here. So let's redraw this. So instead of having a flat oscilloscope screen, I'm going to draw this sort of like that. And so I'm looking at something oblique here. I'm drawing it at an angle so that it looks like we're kind of looking down on it slightly. And associated with that is going to be a magnetic field. Let's see if I can draw that. Okay. Terrible. And we'll just draw a line down the middle. So here is our electric field, getting stronger and weaker, stronger opposite polarity and weaker, stronger, weaker, stronger, weaker. And then our magnetic component, stronger, weaker, opposite polarity, stronger, weaker. And so I've kind of drawn this terrible drawing, but if I look at the textbook drawing here again, you can see it's drawn better. You can see that this wave is showing the magnitude of the electric field and showing that it's vertically aligned, and the magnitude of the magnetic field showing that it's horizontally aligned. Of course, this can be rotated in any way. It could be opposite, but everyone seems to always show the electric field vertically aligned, but you could rotate this any way we want to. And that wave is traveling in that direction. So that's what it's trying to show us. So that diagram that confuses people is merely a graphical plot of the energy, the electrical energy, and the magnetic energy, showing that it gets stronger and weaker, stronger and weaker. Is anything going up and down? No, it's just a graph saying up is stronger, down is weaker. Down is stronger opposite polarity, up is weaker. The other one is the magnetic field. I'm showing it horizontal just to remind us that the magnetic field is oriented perpendicular to the electric field, and that shows that it gets stronger and weaker. Reverses polarity, gets stronger and weaker. So it's just a graph. It's just a three-dimensional way of showing how these fields are oriented, and of course this is a wave that is traveling in that direction. Is this a visualization of what an electromagnetic wave would look like if we could see them? No. This is a visualization of the intensity of the voltage and the intensity of the magnetism, and how the direction that the wave goes is perpendicular to either of those. It's just a graph. So don't be confused by this. It has its usefulness, but it is not a visualization of what electromagnetic waves would look like if we could see them. So what would this look like if we could see it? Of course, once again, we'd have those big spheres. Let's draw one through each peak here. I'm trying to do a cross-section here, and of course, more positive, less positive. Reverses polarity, more negative, less negative. Positive, negative, positive, negative, positive, negative. I didn't do a very good job of drawing that one through the peak, did I? There we go. So that's just showing you the intensity. Remember, that magnetic field is going in like the equator of that circle. It's going to be north one way. Blah, 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 blah. Is that a good drawing? South the other way. Oops, that should be a south. So north, south, north, south, north, south, north, south. And then the next one, north, south, north, south, north, south, north, south. And so this is a terrible drawing, but you get the idea. It's expanding spheres of electricity and magnetism, where this diagram is just showing the intensity, and of course it's traveling in that direction. So that's what electromagnetic waves would be if we could see them. So it's just this field. If we see one coming, If it's from far away, it's just a electric field coming at us at the speed of light. We would see it's more positive one way, more negative the other way. And there's an associated magnetic field that's going to be north on one side, south on the other side, that's going to pass us. And then another wave is going to pass us. How far is it? Depends on the frequency. And it's going to be completely reversed from the first one. And then we're going to get another one that's like the first, alternating, coming past us over and over again as those waves go past us. So just as you can stand on a pier and watch your ocean waves go by, you can see there's a peak, there's a trough, there's a peak, there's a trough. As the electromagnetic waves go by, you can say, oh, there's positive to the top, negative to the top, positive to the top, negative to the top. But they would be going by as big, huge electric fields, not as a wave that you can confine to a physical space. So that is the nature of what electromagnetic waves are, and they act like any other kind of wave. And of course, don't forget that light is electromagnetic waves, just like radio waves are. And they have all the properties of waves. And so they can be reflected, they can be refracted, in other words, bent by going through different mediums. We can use antennas to manipulate the direction that they go. So for example, if we look at the top of a Yagi antenna, I have a different video on antennas. We're looking down at the elements, and we see that these each produce their own waves, but they interfere with each other in such a way that most of the energy, these bubbles, would kind of be stretched, kind of shaped like that. Highly distorted, maybe a little bit going to the back. And so these bubbles are expanding, and they're highly distorted. But still, if we look at any part of it, we'd see that it's more positive, more negative. And if we look at trying to draw the girth of it, south, north, south, north, south, north, we get that same orientation, just a different shape. That antenna is able to shape it so these bubbles go out in that oddball shape rather than as a sphere. Or such as a parabolic antenna, which would take these waves, let's say they're coming from a great distance, so they look parallel to each other, but when they hit the antenna, when they reflect off, they come off and focus to a point, so it acts like a lens. And so that can be done with radio waves, it can be done with sound waves. We can manipulate them just like lenses and mirrors will manipulate light waves. A wave is a wave, and we can treat them all the same. So refraction, diffraction, reflection, bending them, and whatever one wave does, the other one does. And that's important because I'll talk other times about how we can manipulate these waves to get them to go where we want them to go. So I hope that clears up what an electromagnetic wave is. Just think of it as these electric fields going by, and don't forget the associated magnetic field that's perpendicular to that. So I hope you found this useful and informative. If you did, please give me a thumbs up. It really helps the channel. Don't forget to subscribe and hit that gray bell when you do so that you get notified when I put up new videos. And remember that Vocatomy at vocatomy.net is a free online school where you can study electronics technology and perhaps prepare for a career as an electronics technician or get a head start in your studies on electrical engineering. And I couldn't make these videos without the help of my patrons. So to help me put these videos online, you can go to patreon.com/join/Vocatomy. And thanks to my patrons for making this possible, and thanks to everyone for watching.